morning, everyone. We welcome you all to join, who have joined here for today's fifth Lightning Talk series. To begin the session, I would like to invite Ms. Soni Kaul, our principal expert, and good morning, everyone, to deliver the introductory remarks.
Good morning, everyone. The Prime Minister Early Career Research Grant Scheme of ANRF has been launched last year to empower and support early career researchers in their pursuit of research excellence. The scheme provides an enabling environment that encourages them to conduct high-quality research with ease, flexibility, and independence. In its first year, the scheme has been awarded to over 700 researchers across a wide spectrum of scientific fields, enabling them to take bold, innovative approaches to address critical challenges and contribute to advancing India's national priorities. Today, at the fifth session of Lightning Talk series focused on chemical science, we will hear from three researchers from the first cohort of PM-eCRG awardees. Our first speaker today is Dr. Kedar Joshi from Indian Institute of Technology, Goa, who is working on paramagnetic colloids as model system for deformation in 2D materials. Our second speaker today is Dr. 𝗍𝗠𝗘𝗖𝗥𝗚 𝗟𝗶𝗴𝗵𝘁 who is from IIT Kanpur. He is working on synergistic carbon capture and renewables from net zero energy systems. Our third speaker today is Dr. Bharath G, SRM Institute of Science and Technology, who is working on electrochemical pathways for converting CO2 and biomass into clean fuels and chemicals. I now invite Professor Pannurangam Kumaraguru, our moderator for today's session. He is a professor of computer science at IIIT Hyderabad. His areas of expertise span responsible AI, applied machine learning, NLP. Professor PK, as we call him, has been deeply committed to democratizing research, making opportunities and resources accessible to students and young researchers across the country. Over to you, Professor PK. So you're muted.
Yeah. Thank you, Soni, for that introduction, and thank you, Sumita, for setting this up. Thanks, everyone, for joining. I see a few people on YouTube. Hopefully, they will be able to hear us, and everything is okay with the internet. Thanks to the three speakers also. I think I also hope that the audience are able to watch the YouTube channel of ANRF, where we are actually uploading all these conversations in the past. This is the fifth one, as Soni said, and I just looked up the number of views that we totally have. We have already 3,000 views for all the 4 editions that we have had in the past, which is pretty cool for an early career researcher getting on average of 750 hits. Actually, the first one has more than 1,000 hits now, which is very, very nice. And that's where our interest is, to get more sort of visibility for the research that goes on in India, particularly all funding, all awardees, grantees of ANRF. That's the goal here, which we have set up for this Lightning Talk series also. So we'll go in the order of Kedar, 𝗍𝗠𝗘𝗖𝗥𝗚 and Bharath. They will do 12 minutes of each. We will finish all the 36 minutes. And then we'll do the Q&A session. We will take questions for people on YouTube. Feel free to add your questions on the YouTube chat. I will moderate. I'll take some questions from there. We can actually, at the end of it, at the end of the presentation, we can actually have open-ended questions also from anybody. Okay? Kedar, can you share your screen and stop?
Is my screen visible? Is the screen
Kedar.
visible?
Yeah,
Okay.
Kedar, let's go ahead.
Great.
Yes, it is fine.
Good morning, everyone. My name is Kedar Joshi, and today I will be talking about paramagnetic colloids as model systems for deformation in 2D materials. This essentially is sort of reverse of my grant title. The grant title is written there. So what I want to focus today is sort of philosophy behind this project and how I have developed this idea and why we think that this is significantly meaningful and scientifically meaningful. So first of all, I want to thank ANRF for supporting such fundamental research and also for creating this interactive platform to connect with a broad audience. I also want to thank organizers and PK especially for graciously taking time out and making this series possible. So before going further, I want to talk a little bit about how I developed as a researcher. So I'm chemical engineer by training. I did my undergraduate from chemical engineer ICT Mumbai, and then I went to do my PhD from Lehigh University, where I was first introduced to colloidal science. And then I carried forward that research, and I was introduced to active soft matter systems. And currently, I am working as an assistant professor in IIT Goa. And over several years, I have sort of concentrated my research on understanding the collective and emergent behavior of this discrete soft matter system. By collective behavior, I mean that the situations where individual units are following very simple rules, but yet effectively we see very complex pattern emerging from the system. For those who are connecting and are new to soft matter and colloidal science, you can, for this talk, you can consider this basically a system of just a bunch of particles, nano size, collective and emergent behavior in discrete soft matter system. What I mean by collective behavior is the situations where the individual entities are following very simple rules, but as a whole, you see some complex pattern, something like a traffic flow or crowded bus stations and so forth. So I have divided this talk into sort of three segments. And firstly, I will discuss why 2D materials are important and what are the key scientific problems that we can tackle with using this colloidal as model fluids. And using this idea, what type of colloids we're going to use. And in the last segment, I will discuss about what are the actual objectives and sort of questions in this proposal. So this is the big picture, right? 2D materials are central to a lot of technologies, starting from sensors to electronics and energy technology, different energy technologies. I don't have to list all of the 2D materials, but in India, typically, this is directly aligned to a lot of missions, such as semiconductor missions, quantum material missions, then DST program on 2D materials, and so forth. The problem is that the 2D materials are extremely sensitive to any sorts of defects, stress, and strain. They're basically a long lattice of atoms which are arranged in a certain way, and atoms are interacting in a certain way. And small changes in atomic structures can drastically change the performance. Now, what is hard to study here is that in atomic level experiments, it's very hard to study how these defects are moving around, how the grain boundaries are moving around, how the stresses and strain is getting absorbed by the material. The pathways are extremely hard to study experimentally. What we actually see in SEM and TM images is usually the outcome, and the pathway is missing. Now here the simulations are possible and they are quite powerful, but they are limited by scale and they are also very expensive. So I want to emphasize that this is not a study to stop simulations or to contradict any experiments, but this is a complementary study that we want to do. So where are the colloids coming in this picture? And because we are all talking about atomic arrangements and where these particles and nanoparticles are coming in this picture. So if there are any material scientists in the chat, I welcome you all to guess this material. And if you are thinking it's a graphene or magazines, it's not, right? It's basically my background of my LinkedIn profile, which I have just rendered, and these are nothing but 1 micron silicon particles. So what it shows is that you can make similar patterns using particle arrangements, and that's the simple motivation. Now, what is not you're seeing here is that we have to make these colloids interact to each other like atoms do, and then you can see colloids as big atoms. Now, this is sort of not a new idea, colloids as a big atom. There is clear comparison. The atoms are quite small and they are very fast dynamics. So it's very hard to do the direct probing of the atoms, especially in the LIU timeframe. Now, what colloids offer you is that they are sort of million times larger and million times slower than the atoms. So you can directly image them and their interactions are tunable. So you can tune the interactions in which these colloids are interacting similar to atoms. And then what you are essentially doing is you're watching the atomic physics in slow motion. So this is sort of the big motivation for this work. So now you can use any types of colloidal system, and our choice of the colloidal system is these paramagnetic colloids. So I'm just going to briefly introduce what these paramagnetic colloids are. So you consider them as tiny magnets. So when the external field is on, the interactions appear, and when the external field is off, the interactions vanish. So that's the simple sort of rule. Now you can engineer the field around these paramagnetic colloids in such a way that you can mimic atomic interactions. What I mean by in technical words, you can start asking them to interact with each other similar to Lennard-Jones principle. And my work and work from others have shown that if you put a bunch of these colloids, you can see bulk behavior such as phase transformation, as well as some collective emergent properties such as surface tension or viscosity and so forth. So there is very rigorous work which has been done on these paramagnetic fluids. And so far we have done two things. We have understood what are the challenges in studying 2D materials, which is studying the dynamics at atomic scale. And we have seen that the ability of paramagnetic colloids as model fluid to sort of see whether we can tackle these challenges. So this establishes paramagnetic colloids as sort of quantitative model fluids for studying atomic systems. So from here on, I will discuss what are sort of the key objectives of this particular grant and what are we trying to solve. So there are four main objectives here, and the first two are quite similar to each other. We want to understand how this, so we will engineer the lattice of 2D materials using these paramagnetic colloids. And we want to study how that lattice is interacting with external stress and strain, how the deformation pathways are happening in a dynamic mode, not as a static field. And also we want to see from interaction point of view, how the particles are rearranging to accommodate those stress and strain or any sort of deformation in the 2D lattice. And lastly, we want to study sort of bulk behavior. So considering this lattice of particles as some bulk material, we want to extract some bulk properties, elastic properties out of these 2D sheets. So we want to go from particle interactions to particle rearrangements to material properties. And this is how we're going to engineer that. So we will engineer the environment such that we can interact with the paramagnetic colloids will interact as we wish. And you can do that. This is a very well studied system. And the idea is now you can throw a bunch of them and you form these 2D structures with the advantage that you can actually see under microscope what is going on. You can identify different clusters, different crystals, how they are oriented, where are the grain boundaries, how the grain boundaries are moving, how the defects are forming, how the entire crystal is reorienting and so forth. And not like SEMT image where you get a static image. You can do this in dynamics. So you, as the 2D structure is moving, you able to sort of understand how the crystal structure is changing. So the dynamic approach is sort of the novelty. So what are the expected outcomes from this is we hopefully get to visualize what is happening at atomic scale using this model fluid as paramagnetic colloids. We also will get to understand how things go from
Yeah, thanks, Kedar. Ishan, let's start with you, Ishan.
Yeah, okay.
So now, audience, whoever has joined here, you're able to hear everything well, right? Shubham.
Yes, sir, it is audible.
Very nice. Yeah. Yeah, Ishan, let's go ahead.
Yeah, okay. So hello, everyone. I'm Ishan. So thank you, PK and ANRF, for giving this opportunity to talk about my research. I think this is an excellent idea so that, all the people who are not even researchers can find out what we are doing and hopefully get excited about this work. So I'm in the Department of Chemical Engineering. So a little bit about my background. So I did my BTech from IIT Bombay, in chemical engineering. Then I moved to the US. I did my PhD from Texas A&M University, again in chemical engineering. Spent around 3 years doing postdoc. The first was in Wisconsin, Madison, and the second was in Princeton. So moved back to India in 2022 and joined IIT Roorkee for about 7-8 months and then moved to IIT Kanpur. And I've been here since then. So the current focus of our group is on energy system decarbonization and developing optimization algorithms. So the first focus is on the synergistic carbon capture and energy storage system. So why this is important is because most of the literature focuses on carbon capture and energy storage discretely. So they don't consider the simultaneous synergistic effect of carbon capture and energy storage. So in this ANRF project, we are trying to elucidate the benefits of considering both carbon capture and energy storage simultaneously. What are the energetic benefits? What are the economic benefits? And what are the environmental benefits? Another area that we have been working on is energy system decarbonization model development. So as we know, we want to move towards net zero. So India has goal of net zero by 2070. But what are the pathways to get there? The challenge in this identifying what should be the pathway is that the resource availability. For example, here I'm showing solar irradiance availability. So this varies throughout India. So it is not basically uniform. Same thing with wind speed. So wind speed is not uniform throughout India. And also biomass availability is not uniform. Temporally as well, here I'm showing DNI and wind speed. They also vary throughout the day and throughout the year. So in these cases, how do we decide which technologies should be used to satisfy the power and fuel and chemical demand in such that our energy system is net zero? So this project is funded by Schmidt Sciences. So we got recently funding from this agency. And since these two, so primarily my work is in optimization model development. So in general, these models that I talked about before, these models are highly nonlinear, non-convex. So accordingly, to solve them, we are developing novel algorithms. So we are working on algorithms for solving non-convex optimization problems. So non-convex optimization problems also occur in, for example, training machine learning models. And the other focus area is on developing optimization algorithms inspired using statistics and ML for stochastic programming, which is again a class of problems, class of models for to handle optimization under uncertainty. So as we know, we want to get to net zero. So solar energy is one of the, so there are two classes of technologies that can be used. One is renewable energy, for example, solar PV, wind, biomass. The other is carbon capture and storage. So solar energy is one of the promising resource, but the challenge with solar is that it is intermittent. It is not available during the night, but available during the day. So the idea is, of course, you store the excess solar energy and either in batteries, and what we are interested in is storing the solar thermal heat. So this is done by a technology called CSP, which is concentrated solar power with thermal energy storage. And how you do that is, so PV battery, everybody is familiar. You connect your PV system with a battery. When the solar energy is not there, so when solar energy is available, you charge it. When it's not, then you discharge it. So similarly, you have CSP, which works on the principle of using solar thermal energy. So you have a bunch of mirrors. So some solar energy, the mirror reflects the solar energy, then passes on to the receiver where heat transfer fluid is heated up, and you use a power block. So that the heat transfer fluid provides the heat energy to the power block, and excess thermal energy is stored in, for example, here I'm showing 2-tank molten salt system. Now, you must have all heard about photovoltaic and battery, but CSP plus thermal energy storage, maybe you're hearing for the first time. But there has been studies which shows that CSP is cheaper than photovoltaic plus battery. So here I'm showing on the left side, if we require 3 hours storage, what is the cost? What is the levelized cost of electricity on the y-axis? And these are the various years that the LCOE that we can expect. And this is with 3 hours of storage. So what we see is that as the storage hour changes, so for a low storage amount, CSP plus thermal energy storage and PV and battery are comparable. But when the storage requirement is high, so here we have 9 hours of storage, CSP plus thermal energy storage is actually much more cheaper than photovoltaic and battery. And in fact, China is going quite big on the CST technologies. So having convinced you that concentrated solar power versus thermal energy storage can be economical as well as environmental friendly. So there are various ways to store thermal energy. One is sensible heat, the other is latent heat, and the third one is thermochemical energy storage. So thermochemical energy storage are especially promising because they have high energy storage density. So for example, TCS materials can have energy density of 100 to 1500 kilojoule per kg, whereas molten salt have 100 to 200 kilojoule per kg. And that can operate at high temperatures. So we can operate TCS materials at greater than 800 degrees. So what is TCS material? So TCS material are based on storing energy in chemical bonds. So when we have solar energy, you perform a reaction. The bonds are broken. The forward reaction is endothermic. During the night, you combine these reactions, form back the original compound, releasing energy. And that is how you store the energy. And this is a typical configuration of a plant. So, during the day, you heat up your heat transfer fluid, you run the power cycle. During the day, you also perform the forward reaction and store energy in chemical bonds. And during the night, you do the reverse reaction, provide the heat to the power cycle and generate power. So this is the working principle. Now, there are still challenges with CSP TCS that we showed in our previous publications, that the electricity price for CSP TCS is still almost double than the current electricity price that a consumer pays in India. The primary reason for that is that they have low energy density compared to fossil fuel. So here the energy density of TCS material is about 100 times less than fossil fuels. So for example, natural gas has around 40 megajoule per kg of energy, whereas highest TCS materials can do is 1500 kilojoules per kg. And we also have limitation related to temperature. But the advantage is that there is very low carbon footprint. Once we have set up this plant, we are not burning anything. We are not burning any fossil fuel. So it has low carbon footprint. So this brings me to the new configuration, the project, the NRF project that we proposed. So we proposed a new process called offset process. So what we are doing here is we are doing the forward reaction based on redox system. So we have NXOZ, some metal oxide. We are reducing it to another oxidation state, MXOY, and we are storing the excess oxygen. And during the night, what we are doing is we are coupling the thermochemical energy storage system with a fossil fuel energy combustion, energy-based production. So here what we are doing is we have similar TCS material giving us the energy during the night. And we also use this stored oxygen to burn fuel. Why do we do that? Because we get pure CO2. Yeah. So when you burn coal in a fossil fuel plant, you get nitrogen as well. So there is carbon capture technologies which is used to separate nitrogen and CO2, but that becomes expensive. So since we only burn coal or natural gas, or in fact, even biomethane, if we burn in presence of oxygen, we get pure CO2 and steam. That steam can be, CO2 and steam can be easily separated. So there is very less energy penalty. So this is the basic idea. And yeah, so the advantage is that we have high energy density operation during the night. So natural gas is being combusted, which has high energy density. But the advantage is that since we are burning in the presence of pure oxygen, carbon capture happens, and we don't really pay a huge, we don't emit any CO2. Yeah. So since we have CO2 and steam, which can be easily separated, and CO2 can be stored. So why do we need optimization for this process? So we know from our thermodynamics that we need high power cycle temperature, but we cannot have very high power cycle. So let's say we have high power cycle temperature, that will require very high heat transfer fluid temperature, high receiver temperature. High receiver temperature means radiative losses, meaning the receiver efficiency, as I've shown here in orange curve. So the orange curve shows how the receiver efficiency changes as we increase temperature. Receiver efficiency drops down, power cycle efficiency increases. So there is some trade-off where the optimal temperature should be. Okay, and here we again, other trade-off here is that we want to store oxygen. Oxygen is a gas. If we don't compress it, we'll require a huge storage tank. So we need to compress it. Compression requires power. If we compress it a lot, we consume a lot of electricity. So there is again some trade-off here. What should be the compression cost? What should be the storage tank requirement or volume required? And we also have design decisions. For example, how large, given some demand, how large should be our solar field area, this heliostat should be? What should be the reactor sizes? What should be the storage tank sizes? And also operational decisions. How are the mass flows happening? What should be the temperatures of operation of these reactors? How much is the storage material required? How much is the fuel requirement? How do we charge and discharge? Another question that arises is, what if we take advantage of the power, the electricity market? Can you hear me?
Yeah, Ishan. I was going to say,
Okay.
can you wrap up in a minute or two? Yeah.
Yeah, sure. So So one question that arises is, so if we have a CSP operator, so we know since 2020 there is a new policy framework which allows to trade electricity. So during some time of the day, the electricity price is low, and some other time, the electricity price is high. So we are going to provide the developing model which provides the solution. So which involves designing the plant as well as operating the plant such that the profit of the CSP operator is maximized. The challenge with these problems is that the DNI, the solar irradiance, which is the resource that is required, varies throughout the year and also varies throughout the day. So how do we design such plants? The electricity price, for example, also varies throughout the year and throughout the day. So what should be the operating schedule? How should we operate these plants? So that is where the optimization is needed. And so that is one challenge. The second challenge is, so we have these bunch of other technologies also, right? Photovoltaic, CST, which have some cost, right? So CST actually costs double than the photovoltaic. And wind turbines are even cheaper than photovoltaic and wind turbine, CST. And nuclear is much more expensive. So as we are hearing from the news that, India is going to have, around 200 gigawatt of nuclear by 2047. So how does this offset process that we have proposed, where does it contribute? So for that, we are going to develop something called a superstructure-based framework, which considers the performance of various technologies and which will tell us what is the minimum cost of technology, the installation capacity of technology, the operating schedule to satisfy the demand. Yeah, so these are some results where we have shown that the offset process cost is lower than the CSP TCS cost. And CSP TCS ASU is where we have oxygen provided by air separation unit, which is a standard way to provide oxygen. And we show that our technology, our offset process cost way lower than the other technologies. And so societal impact. So first important is the skill development of the students working on this project. So the student working on this project will get familiarized with techno-economics, life cycle analysis, optimization, under uncertainty, global optimization, then ML models. And it will contribute to net zero emission target of Indian government. And once we have success with this project, we want to build a prototype in the lab, showing how this. So this study is primarily computational, but we want to build a prototype later on, and hopefully commercialize that at some point of time. And ultimately, the computational tool that we will develop, the power companies can possibly use it to take advantage of time of day tariff that has been introduced. So yeah, so I'm looking for so students can reach out to me via email. I'm looking for students, postdocs, MTech students, and so this is my Twitter handle, and this is the LinkedIn profile. So with that, over to you, PK.
Yeah, thanks, Ishan. Bharath, let's start, Bharath. For the audience, feel free to keep your questions ready. When Bharath is done, we can actually get you to ask questions. I also have some questions. We can take it. Bharath, 12 minutes, Bharath.
Yeah, my slides are visible.
Yeah.
Okay. I thank our CEO and Professor PK for organizing this lightning talk series for our early career awardees. And I would like to thank all the NRF members also. So this is like my professional academic. I received my PhD from Bharath University, Coimbatore in 2015. Then I moved to Japan, UAE, Saudi Arabia, and then Chile. And almost 2015 to 23, I spent there as a research scientist, postdoc, and then visiting researcher to that country. And then 2023, I joined as a research assistant professor in SRM Institute, Katangulathur. And then I'm successfully running one research group, that is a sustainability research laboratory. And then under my guidance, 4 full-time scholars are working, and then 1 JR from this yearly career project. And I'm having almost 140 plus publications, and my Kutch index around 56, and then 8,500 plus citations I have. And I'm specializing especially in my group. I'm working on different field, for example, CO2 capture and conversion, and green hydrogen and ammonia, and then clean energy, biomass utilization, and advanced catalysis. So this is like SRL lab, sustainability research lab at SRM IST. We are working on sustainable carbon and energy research. So three themes. So first theme, carbon capture and conversion. We are capturing CO2 and then we are converting CO2 into fuels and chemicals. This is one major objectives in our lab. And green hydrogen. So we are generating also green hydrogen, and we are storing green hydrogen in the form of ammonia. We believe that ammonia is one of the practical hydrogen carrier in future. And also biomass conversion and valorization process, because we know India is agricultural land. We are producing tons of agriculture waste. We are just dumping those all waste into that land, and also we are polluting. So how we are successfully utilizing this biomass conversion valorization into some organic molecules or fuels. So for those three applications, we need to develop an advanced catalysis process. What advanced catalysis process? Especially we developed a different single atom based catalyst that deposited on MOF and then 2D materials. We are using these materials to develop an advanced electrodes for bifunctional applications for carbon capture and conversion, green hydrogen, ammonia energy carriers, and then biomass valorization. We are using those advanced catalysis. So we know that the national motivation, we committed net zero emission by 2017, and then we are facing three interconnected challenges. So first, CO2 emission. Continuously we are producing, we are emitting CO2. That is also one of the important problem. And then biomass burning. So agriculture, almost 500 million ton we are producing bio waste, and then almost 100 million ton we are just burning that biomass. So this is also contribute to the major global gas emissions, and also imported fossil fuels. So these three major challenges, how I'm going to address, especially through our research. For example, solution one, the CO2, we are just capturing the CO2 from industry, then we are converting that CO2 into renewable fuels. For example, if you want to convert CO2 into chemicals, then you can also convert, for example, CO2 and then NH3, you can end up with urea, and then CO2 plus H2, you can end up with CH4 gases. Or if you want to convert the CO2 into fuels, then that electron, proton, that photon based reaction involved, then you can convert that CO2 into fuels and other chemicals. In the second, agri waste. So we are using that agri waste. Then we are doing the pyrolysis. We are end up with the char, bio oil, and then other gas products. So the bio oil, we are taking that bio oil that we are using for liquid organic hydrogen storage medium. So that is also one of the important things. We are successfully utilizing this bio oil. So we are end up with indigenous clean fuels for energy security. So this is one of the national motivation also. So based on this research, I proposed this research especially for next generation photoelectrochemical flow reactor for efficient CO2 reduction as well as bio-oil valorization. This is for India's carbon neutral energy future. And then we successfully received this project also. I thank really enough for supporting this wonderful research. And then the overall objectives of the project, that is integrated electrolyzer flow reactor. So one reactor that may be useful for converting CO2 into fuels, and then same reactor we can also use for bio-oil upgradation or bio-oil conversion. So that is one flow reactor we are developing. So for that also, this is like a typical flow diagram. So pyrolysis, through the pyrolysis, biomass converted into bio-oil. That bio-oil, that is feed for the photoelectrocatalytic reactor. And then we are capturing the CO2 from air or where the sources. Then we can collecting the CO2, and then we are supplying the CO2 into this reactor. This reactor is able to convert CO2 into fuels, as well as this same reactor converting fuels, because the electrochemical chamber, two chamber, one anodic chamber and other cathodic chamber. So cathodic chamber, we can performing CO2 reduction. In the anodic chamber, we can also able to perform bio-oil upgradations. So this is like complete mechanism. So for this, we need to develop an advanced catalyst. Those catalysts should be work for longer time, minimum 1,000 hours. So in that case, we developed a single atom deposited catalyst on 2D materials. And then we are also developing many catalytic materials. Recently, we published papers also related to single atom catalyst. And then this single atom catalyst, we developed on 5 functional electrodes. That electrodes will be used for both anode and the cathodic material. We can perform biomass conversion also, as well as CO2 conversion also. Okay, let's come to the biomass screening and utilization. So we know that India is agriculture background, and then we producing tons of bio waste. That agriculture waste containing chemicellulose, cellulose, and then lignin content. When we processing acid catalysis process, we can also able to generate lot of chemicals, perfluorol and then 𝗪-cresol. So many bio-derived compounds also we can produce. And then through the pyrolysis also, we can able to generate bio oil, 35 to 48%, and then 20 to 25% gas, and then 35% biochar, that is feed for activated carbon production. So once we developed an perfluorol from bio waste or any chemicals from bio waste, and then we also obtained pyrolysis oil. So pyrolysis oil, that is bio oil, that is highly oxygenated compounds. So we can use this both oil to convert into fuels. How we are going to convert? That is electrochemical parts going to enter. So if you do hydrogenation, then you can end up with biofuel. If you do oxidation of biomolecules, then you can end up with renewable polymers. For example, perfluorol, if you convert perfluorol into FDCA, that is polymer precursors, that may be end up with plastics. So biomass, screening of biomass, very, very important, because currently we are collecting and biomass from South Tamil Nadu and then North Tamil Nadu and then Kongu belt, and then we are characterizing those biomass. What is the composition of hemicellulose, cellulose, and then lignin content, and then how we are going to produce chemicals from those biomass. So that is also one of the important thing. And then we recently produced a bio oil. That bio oil also we successfully upgraded, and then we are getting a higher heating value that is more relevant to the biofuel. And then what is the benefit for farmers and rural communities? Okay, at least minimum per ton, we are able to generate at least 15,000 to 30,000. It will help to the farmers. So this is one of the important farmers and the rural communities applications. So once we developed an pyrolysis oil from bio waste, then that is a feed for our reactor. So this is like the complete photo electrochemical reactor, electrolysis reactor. Then we are planning to build 1 kilowatt flow electrolyzer, that stackable electrolyzer, that is continuously operating CO2 conversion in the cathodic chamber, and then the perfluorol or any other bio oil derived compounds oxidation in the anodic chamber. So this is the complete working model. So this is flow reactor. This is like a flow reactor, not an one single static reactor. So we continuously supplying a CO2 to this reactor. This reactor is continuously converting the CO2. Once we collecting the product, converted product from the reactor, then we having a lot of next steps, because we need to further purify the chemicals. Suppose if I convert the CO2 into methanol, then I need to purify that methanol components from that reactor. So this is the thing. And then also I can able to convert perfluorol into FDCA, that is polymers. So this is our ultimate aim of the operating parameters. So we are buying one by one all accessories. At least in the end of our project, we can able to generate 1 kilowatt flow reactor that will continuously operating conversion of CO2 into fuels. So what is the project deliverables? Yes.
Bharath, 1 or 2 minutes, Bharath?
Yeah, almost finished, sir.
Yeah.
So what is the project deliverables to obtain sustainable India? So first deliverables, National Biomass Intelligence Platform. So India-wide biomass characterization database we are going to create. And then region-wise feedstock suitability map. And then we are going to include all the parameters. For example, what are the composition, the yield, and then conversion potential. And then support for industry, micro, small, and then macro enterprises. For example, process engineering package for pyrolysis reactor we support. And then bioil quality, so because the industry developed biofuel, maybe they produce biofuel, but they don't know how to characterize it. We can also support that, how to characterize, and then we can also analyze that bioil, that fuel grade analysis, fuel grade. And then guidance for local enterprises and industries. And also we can able to develop tons of activated carbon that is highly porous activated carbon, high surface activated carbon. We can use also supply this activated carbon to water purification and then energy storage, battery, and then capacitor applications. And then the CO2 conversion process also, the demonstration capacity at least 10 liter volume per hour we need to reduce, and then we can able to provide the clear roadmap towards pilot scale deployment. So this is like the CO2 capture and then conversion system. So market ready output from our research, simple. So we definitely produce a high grade bio oil and then biofuel from our research. And then this bio oil is one of the important liquid organic hydrogen carrier for the future, and at least we can able to 5 to 6% to 8% we can able to store hydrogen. And then activated carbon, of course, tons of activated carbons we can produce. And then CO2 derived fuel also we can able to generate. And then polymers, bioplastic precursors we can also develop. And then technology service, of course, the process package for pyrolysis and upgrading to the industry. And then fuel grade testing and then product analysis. So that is also we can support. So this is like market ready output from our research. And if anyone want to collaborate with us, and also if any students, PhD students or master students, you want to do the research on CO2 conversion or biomass conversion or bioplastic production, then you can also join with us. So thank you so much. And then together let's build a sustainable India. And then thank you, James. Thank you so much for PK to organizing this wonderful lightning talk. Jai Hind.
Thank you, Bharath. Thank you, Kedar, Ishan, and Bharath, all three of you for your deck of slides. So I have one or two common questions. Questions let's do in the same order, Kedar, Ishan, and Bharath. I'll do one or two, and then we can hear if others who are on the call, if they have any questions. So can three of you speak about, I think each of you mentioned about some things, but I wanted to make sure that gets captured. If somebody is interested in working with you, what skills are you looking for? What would you write as a job description for the student who needs to work with you?
Self-interest. Motivation, self-motivation and interest.
Okay. Kedar, Ishan?
No, I welcome students definitely who are interested in soft matter, chemical engineering. Computational modeling is also relevant. I think the background in chemical engineering or applied mathematics is useful, but as he said, most importantly, the curiosity and willingness to work in interdisciplinary is, I think, most valued.
Okay, let's do Ishan.
So, yeah, very much interest in maths, chemical engineering, and debating. So we work in this, what we ask questions a lot of time, what technology is low carbon? So really going into being curious about it and, really going into the debate. Don't be afraid to speak your mind. And yeah, of course, interest is needed.
Okay. Very good, very good. Each of you have interesting points about curiosity and everything. Okay, we can keep that for a separate discussion, broader discussion, I guess. But are there any pressing questions from Sen Gordon, Shubham, and Brunta? Any questions from any of you? Please raise your hands up in the Teams, and then we can take a question. But let's do a few questions with the speakers. So Kedar, let's do with you, Kedar. So I think this question is probably valid to all of them, but let's do one question about, so let's take, your project is for 2 years, I assume? 2 or 3 years?
3 years.
3 years. So let's assume that 3 years is done. Now it's January 2029. Give me some understanding of what set of people will benefit from your research? What will change in anybody's life?
No, that's very important question, especially because this is sort of a blue sky research, which is mainly driven by the curiosity, but it does affect a lot of research areas. And I can say this outright: this research does not really promise a device, but the main part is to have understanding that enables better devices. So I think the fields which are directly impacted are maybe material physicists, a lot of soft matter, condensed matter communities, uh, and it mainly is going to bridge gap between the atomic simulations, people who are doing atomic simulations, and continuous models, because atomic simulations are expensive, but it's hard to scale. You can't do too many of them. And continuous models are, it's very hard to validate them. If you want to say something is a bulk material, and when the time scales are really small, the continuous models, usually it's very hard to validate. So those gaps, I think it will help to bridge. And I can think of few technologies which which are directly affected. First of all, a lot of flexible electronic devices are 2D materials these days. A lot of nano and micro electromechanical, which are broadly classified as NEMS and MEMS. So those are 2D materials. And in energy applications, a lot of electrodes and membranes, they are particularly because they constantly go under this stress and strain environment. So how their dynamics is affecting. This is I think these areas are important.
Very good. Very good. So yeah, I see Dr. Shubham having a question. Go ahead, Dr. Shubham. Please ask a question. And if it's targeted to any one of them, tell us who are you asking the question also.
Good afternoon.
So let's go to Ishan for you. So I think you talked about CSS, offset, all that. Can we not do this retrofit with all the existing things and change everything that we already have? How much difference will it make? What does it mean to retrofit?
Yeah. So do you mean to ask that if we retrofit with the carbon capture, the existing coal plant?
Yeah. Correct. Yeah.
So yeah, I mean, sometimes people debate that, there are already we have assets which burn natural gas and coal, and retrofit them with carbon capture technologies. Why are we worried too much about why are we worried too much about this renewable energy, because storage is so expensive? So the reason behind that is so that the answer to that question lies from life cycle analysis. So life cycle analysis tells us that when you even extract coal or natural gas out of the earth, there are unabated methane emissions. Unabated meaning that we cannot capture them. And methane has 80 times higher global warming potential than CO2. So we cannot simply rely for only carbon capture. Of course, they have a role to play in hard to abate sectors, but we cannot simply retrofit because the emissions will be continuing. We will not be able to reach net zero. So we will be able to reduce emissions, hopefully, but it will not be net zero. And the carbon capture is not 100%. It's going to be 90% CO2 captured, plus this upstream methane emissions that are happening, which remain uncaptured.
Very nice. So there's a question in the chat also, but before that, I had a very minor, just for understanding, I guess. When you showed the graphs for the hours, right? The cost. So you showed the graph for the 5 and a 9 hour. Is that a window that people study? Why 5 and 9 are important?
Yeah. So 3 and 9 were the numbers.
Oh, sorry. 3 and 9.
Yeah.
So I wrote it down. Sorry.
Yeah. So solar energy is typically available for 8 hours or 9 hours max. So for the remaining hours, you will require some amount of storage. So typically you will require more than 3 hours. But this is only to show that batteries will only work for small storage hours and not for longer ones. That was the reason. And typically we will require more than 9 hours storage.
Okay. So, Ishan, do you want to take the question in the chat? It says, Sen is asking, since solar panels will eventually reach end of life and become waste, do you have a contingency plan in place?
I mean, this is an active area of research. So, people are talking about, and research is happening on recycling this photovoltaic panels. So, of course, like if we just ignore it, we'll have a pile of solar panels which will probably reach the moon. We'll have to have recycling technologies, and people are working on it. For batteries,
very nice.
For example.
Yeah. So, Sen, that's a very good question. So, Ishan, just give us some understanding. So, what is the so to say lifetime of a solar panel? I see all around the campus that they keep, but when do they have to throw it away?
I mean, the efficiency keeps on reducing, but after 15 to 20 years, you have to throw them away.
Okay. That's a good question. No, then I think it must be a very hard question also to study. I mean, you build all of this, 15 years you have to throw it away. Then what do you do with them also? Okay, very good. Great questions, and let's go to Bharath. Bharath, one or two questions for you. Since you're collecting, so to say, these biomass, currently I think you said you're collecting from Tamil Nadu. So given the diverse, so to say, nature of India, do you see any, so to say, challenges for when ANRF is funding projects to see adoption and scale, impact in the country, all that, right? Given your research in Tamil Nadu, tell us about how can it be used across the country?
Yes, Professor. Actually, that is, we are continuously collecting the biomass from various places. The same coconut shell I am collecting Salem, and then same coconut shell I'm collecting in some Congo belt, for example, Coimbatore, and then Pollachi. So the composition, the cellulosic composition, lignin composition, almost 10 to 15% changes when I'm collecting these biomass. So if I just estimate the bioil production yield and then biochar yield based on the lignin, cellulosic, and then hemicellulosic content, so I can also get some trouble because wherever I'm collecting biomass, it is giving different composition. So that's why I want to make one library so that each place wherever I'm collecting the common biomass, so that I want to record what type of composition present in that particular sample collected from the particular area.
Very nice. So, but still, Bharath, the places that you are saying is all still in Tamil Nadu. Is there an effect if you do the same thing, let's take in Kanpur or in Goa?
Yes, actually, I proposed all over India for collecting the biomass.
Okay. So continuing on this, it's a little bit about all the policies, right? The government of India has policies around whatever stubble burning, regulation, all that is coming, right? I mean, how would you? I mean, given your research, it looks like you're really hooked into the sort of say last mile people also. Farmers and doing all that. I mean, how do you give us some ideas about understanding of these farmers, of these regulations, policies? I mean, do they understand? Do they stubble burning and things like that? Tell us some thoughts about all that.
Yes, Professor. Actually, I'm having a plan to conduct a workshop. So that workshop, I'm going to bring some Panchayat leaders who is more active in agriculture and small industries. So in that workshop, we are going to explain about the farmers should not burn the things, bio-waste, and then instead of burning bio-waste, then we can convert them into biomass and then value-added products. So in that workshop, we are going to explain to the farmers, because I'm also basically coming from farming background. Still, I'm doing farming. So I saw many of farmers still they're doing, burning the bio-waste and then they're polluting the environment. So I want to stop these activities. So that workshop may be helpful. The next year we are planning to conduct it.
Okay. So that's the workshop that you're planning. My question was more along the lines of what's that. But let's move on. This question is to you and Ishan together. Let's go to Ishan and then you can answer it after taking a break. Both of you talked a little bit about commercialization, right? Commercialization of your work. So do you 3 years from now, let's take you have some understanding, implementation, all that. What kind of challenges do you see in your individual disciplines? I'm not interested in hearing the generic challenges about commercialization in India, which is probably by itself a topic of discussion. But in your specific disciplines, do you see any challenges and do you see that anything needs to be unblocked for those challenges?
Yeah,
Ishan.
so the work, so I can start. So the work, the focus of this work is primarily on concentrated solar thermal. But in India, for whatever reasons, that technology has not picked up. So people have been talking more about photovoltaic plus battery. But I mean, there has to be some discussion with industry, like why are you focusing on that versus, CST plus thermal energy storage. And so one of the things that I think which can be used by industry in our work from the output of this project is the scheduling and design of renewable energy systems. So although we are doing it for CST, but it is applicable for other renewable systems because they are also intermittent, and that question about when to charge, when to discharge, given some power demand and some electricity price, how do you schedule the operations and design these plants? So one major bottleneck that I can see is like getting in touch with the industry guys. So those kind of conversations don't happen that easily. And I mean, although that is one major challenge. Like, although sometimes we work in silo, we think that okay, this is important, so we focus on one part, but maybe the industry requirement is something else. And although we have the capability to deliver that, but because there is always some difference in what we think and what they think.
I think that's an important problem. I think those differences are reducing thanks to a lot of activities, but it's still the linkages between what you do and what industry wants is slightly difficult to get it. Okay, Bharath, your answer for that?
So my answer after the project, simple, Professor. So suppose we are producing tons of biofuel, where I can sell this. So that's questions. So I want to identify the buyer, first of all. Then I need to connect the farmers, industries, and then buyers. So this triangle, I need to work on that.
Right.
So that may be challenge after the project. I will check.
So that's what probably Sengodan also is saying about, can you give it to can you pay farmers to do whatever you're recommending to do? That's pretty good. So let's just stop in a minute or two. Any last thoughts from each one of you? 30 seconds from each one of you. What would you want to say? Let's go in the same order as we started. Kedar, Ishan, and Bharath.
No, I think it's this is for the lightning talk series or in general?
Yeah.
So
anything.
No, I think
it's 30 seconds to say whatever you want to say.
No, I think having these kind of discussions is wonderful. As a researcher, you always are sort of in your shell and doing small specified problems. To connect with different researcher and really see what the national priorities and what other people are doing is
very nice.
Bringing different people into a picture is very helpful.
Very nice. Yeah, Ishan.
Yeah, I mean, this is a really nice lightning talk. I mean, I think this allows us to connect with the broader community, outside our bubble of researchers. We meet each other in the conferences, but, hopefully some, as a kid, if somebody watches these videos and get inspired to be work in core and engineering and So if that thing happens, even if, one student sees and see, oh, this seems interesting, I want to work on this, that's a success.
Absolutely, Ishan. Very nice. Bharath?
So this is very interesting platform for sharing our knowledge. So the researchers also may understand what is the ongoing research and then basic research problems, where should they pick the research problems. I really thank, and also I thank, I also got 𝗟𝗟 project that related to ammonia energy carrier. Hopefully, maybe I will give another one talk if PK arrange for 𝗟𝗟 people also.
Yeah, I was going to say a few things. For your sort of say knowledge, if nothing else. So one, I think there's some discussion about. So this is online. We wanted only this one because I really wanted only like 1 hour slot for this. Unfortunately, today it went beyond. But 1 hour, 10-minute slot where we give ideas. You present, ask some questions, and then we stop. But there's also internal discussions about, can we make a sort of say a Goa ANR of day or a Kanpur or a Delhi ANR of day where all PME, CRG, NPDF, ARG, all grantees come together and something like that can be done. There's discussions going on. Hopefully, we'll see how far we can get. Given that this was easy to set up, online requests, get you present, all that. This is the first starting point. But there's already 2-3 things you will hear in the next month or so. There is some internal discussions going on a few things about it. That's my first plug. My second plug is about so if you maybe you've heard about it, but please continue talking about your research on social media. Tag 𝗟𝗟, tag Dr. Shiv, all that. Whenever you have a content that is pushed outside, which is in the format of a patent or a paper. I just posted the link of the 𝗪𝗏 also. Feel free to use 𝗪𝗏 also as part of the dissemination of the knowledge. What Ishan said, right? Spark of some people looking at this video. The sparks can come from many different ways. That's all I had. I'm going to give it back to Sumita and Sony, and then we can wrap it up.